This video will look at how your data science workflow can be impacted by the way in which you organize your code. We've already described how we might organize an effective data science project at the level of a directory or a file. In this video, we're going to delve one step deeper and consider how we can structure our work within those files. In particular, we'll be focusing on code files here. We'll start by comparing the two main approaches to structuring our code, namely functional programming and object-oriented programming. We'll then see how we should order code within our scripts and see some conventions on how to name the functions and objects that we work with in our code. We'll round up this video by summarizing the main points from the R style guide that we'll be following in this course, and highlight some useful packages for writing effective code. First up then, let's meet the functional and object-oriented approaches to programming. A functional approach to programming has two major properties. Firstly, the original data or objects are never modified or altered by the code. We've met this idea before when making new, cleaner versions of our raw data, but leaving the original messy data intact to work with again in the future. This property of object immutability is the exact same idea, but in a coding context rather than in a data context. In functional programming, complex problems are going to be solved by decomposing them into a series of smaller problems. A separate self-contained function is then written to solve each subproblem, where each function in itself is simple and easy to understand. This makes these small functions really easy to test and reuse in many places, and code complexity is built up by composing these functions in various ways. It can be quite difficult for a lot of people to get into this way of thinking, but people with mathematical training often find it quite natural. This is because mathematicians usually have many years of practice working with function compositions in the abstract mathematical sense. One issue with functional programming is that lots of nested functions mean that there are also lots of nested brackets. These start to get really quite tricky to keep track of when you've got upwards of 3 functions being composed together. This reading difficulty is only exacerbated if your functions have additional arguments on top of their original main inputs. The pipe operator from the Magritte R package tries to help us with this issue. It's written as a %, followed by a greater than, followed by another %, and it works exactly like function composition does mathematically. It takes whatever's on the left, whether that's an object or the output of a function, and it passes it to the following function call as the first argument of that function. The pipe operator is often referred to as syntactic sugar, and this is because it doesn't add anything to your code in itself, but rather it makes the code so much more palatable when people are trying to read it. One thing to note here is that in R versions 4.1 and higher, there's a built-in version of this pipe operator, and this is written using a vertical bar symbol followed by a greater than sign. Just to cause confusion, the vertical bar symbol in itself is also called the pipe symbol in more general programming contexts, and to type this vertical bar, you can usually find it above the backslash on your keyboard. In most circumstances, the base R pipe is going to behave in the same way as the pipe from Magritte R, but there are a few cases where they differ. For reasons of back compatibility and consistency, we're going to stick with using the Magritte R pipe in this course. Pipe operators are designed to put the focus on the actions that you're performing rather than the object that you're performing those actions on. This means that there are 2 cases where you should almost certainly not use a pipe. The first of these is when you need to manipulate more than one object at a time. Of course, using secondary objects as reference points but leaving them unchanged is perfectly fine, but pipes should be used when applying a sequence of steps to create a new modified version of a single primary object. Secondly, just because you can chain together many actions into a single pipeline, that doesn't necessarily mean that you should be doing so. Very long sequences of piped operations are truly easier to read than nested functions, but they do still burden the reader with an equivalent cognitive load on their short-term memory. Be a kind programmer and create meaningful intermediate objects with informative names to help the reader of your code. This will help them to more easily understand the logic within your code, as well as improving the readability of your code. The alternative to functional programming is then going to be object-oriented programming. When we're taking a functional approach, we solve complicated problems by using lots of simple functions, while in an object-oriented approach, we solve complicated problems by using lots of simple objects. Which of these programming approaches is going to be best will depend largely on the particular type of problem that you're trying to solve. Functional programming is excellent for most types of data science work, but object-oriented really comes into its own when your problem has many small components all interacting with one another. This makes it really great for things like designing agent-based simulations, which I'll come back to as an example in a moment. In R, there's 3 different systems for doing object-oriented programming, so things can get pretty complicated. I'm not going to go into detail about them here, but I'll give you an overview of the main ideas, which might be useful in the future. For example, if you want to extend base R functions so they work with new types of input and to have user-friendly displays. In this case, Advanced R by Hadley Wickham is going to be a really excellent reference text for you. In an object-oriented program, each object within your script belongs to a class and has a set of methods associated with it. An illustrative example might be when creating an agent-based simulation of a beehive. A class here defines what an object is, and methods describe what that object can do. On top of this, each object has class-specific attributes or data fields. These fields are shared by all objects in a class, but the values that they take give information about that specific instance or object. If you're thinking this all sounds very abstract, you'd be right. So let's make things more concrete and consider writing some object-oriented code to simulate activity within a beehive. In our code, each object will be a bee, and each bee is an instance of one of 3 bee classes. It might be a queen bee, a worker bee, or a drone bee. The different bee classes have different methods associated with them, which describe what that bee can do. For example, all bees would have 6 methods that let them move up, move down, left, right, backwards, and forwards within the beehive. An additional reproduce method might only be defined for queen bees, and an additional pollinate method might only be defined for worker bees. Each instance of a bee is going to have its own data fields, which give information about that specific bee. Every bee is going to have X, Y, and Z coordinate fields to give their location within the hive, but the queen class might have an additional field for their number of offspring, and the workers might each have an additional field for how much pollen they're currently carrying. As our script runs and our simulation progresses, methods are applied to each object as the bees move around the hive, collect pollen, and reproduce, and these methods alter the field values as well as potentially creating or destroying new objects, or bees. This is really different from the preservation mindset of functional programming, but hopefully you can see that it's a very natural approach to take in many types of problem. Okay, that's the 2 overarching approaches to writing code covered. Let's dig into the detail now and give concrete guidance on how to structure your R scripts. First things first, let's discuss what should be at the top of your R script. It's almost always a good idea to start your file with a few commented out sentences that describe the purpose of the script. And if you're working in a large team, maybe add who to contact with any questions about that script. There's more on questions coming up soon, don't worry about that. It's also good practice to move all of your library and source calls to the top of your script. These indicate the packages and helper functions that are the dependencies of your script. So it's useful to know what you need to have loaded or installed before trying to run any of your code. That actually segues us nicely into the next point, which is never to hard code your package installations. This is extremely bad practice and very rude to do, because then your R script might alter another person's installation of R. If you don't know already, this is precisely the difference between an install packages and a library call. Install packages downloads the code for that package to the user's computer, while library takes that downloaded code and makes it available within the current R session. To avoid messing around with anyone else's R installation, you should always type your install packages command directly into the console, and then place the corresponding library calls within your script. Next up, it's likely that you or someone very dear to you will have in the past committed the felony of starting every script by setting your working directory and clearing R's global environment. Again, this is very bad practice. It's indicative of a workflow that's not project-based, and it's problematic for at least two reasons. First, the path that you'll set is likely not going to work on anyone else's computer. Secondly, clearing the environment like this may seem like it gets you back to a fresh, new R session, but all of your previously loaded packages are still going to be loaded and lurking in the background. Instead, if you want to achieve your original aim of starting a new R session, then go to the menu within RStudio, select the Session dropdown, and then select Restart R. Alternatively, you can use keyboard shortcuts to do the same thing. This is Ctrl-Shift-0 on Windows, or Command-Shift-0 on a Mac. The fact that these keyboard shortcuts even exist should quite strongly hint to you that in a reproducible and project-oriented workflow, you should be restarting R quite often in an average working day. Finally then, let's circle back to that point I made earlier about setting the working directory. The reason this won't work is because you're likely giving file paths that are specific to your computer, your operating system, and your file organization. The chances of someone else having all of these things the same are practically zero. So let's see what we can do about it. To fix this problem of person and computer specific file paths, you've got two options. The first is to use something called relative file paths. In this case, you assume that each R script is being run in its current location, and by moving up and down through the levels of your project directory, you point to the file that you need to load. This is good in that it solves the problem of file paths breaking when you move a project to a different location on your own laptop. However, it doesn't fully solve our portability problem, because you might move your file to a different location within the same project. It also doesn't solve the problem entirely because macOS and Linux operating systems use forward slashes in their file paths, while Windows uses backslashes, so your code will still break if it gets moved onto a computer with a different operating system. To resolve these final two issues, I'd recommend using the here function from the here package. This package looks for our project file or a Git file to identify the root directory of your project, and then creates all file paths relative to the root of your project in a way that's suitable for the operating system that your code is currently being run on. This really is some quite marvelous functionality. For more information on how to use the here package, feel free to explore its documentation and its vignette. Moving on now, we'll go from the head to the body of the code. This section is designed as an introduction to the tidyverse style guide, and as by no means a replacement to it. Having well-named and organized code is going to facilitate both reading and understanding of your work. Comments and sectioning then do the rest of this work for you. Comments may either be short inline snippets at the end of each line, or a full line dedicated in itself to a comment. To create either type of comment in R, simply type a hash followed by one space. The rest of that line won't be evaluated and will function as a comment. If you need multi-line comments, simply start multiple lines with a hash and a space. As simple as that. The purpose of these comments is to explain the why of what you're doing and not the what. If you're explaining what you're doing in most of your comments, then you maybe need to consider writing more informative function names, something that we'll return to in the general advice section soon. Comments are also a really good way of adding structure to your code, and you can do this by using commented lines of hyphens and equal signs to chunk your files into major and minor sections. Within these titles, markdown-like section headers can be added to define these sections and subsections of your code. If you use these, many IDEs like RStudio will interpret them as a table of contents for you so that you can more easily navigate around your code files. When creating and naming objects, a strong guideline here would be that objects should be named using short but meaningful nouns. Names shouldn't include any special characters, and words within those names should be separated using underscores. This is kind of similar to our file naming guide, but note that we can't use hyphens in our R object names, because this is going to conflict with the subtraction operator. When naming your objects, as far as possible, try to use singular nouns as well. The main reason for doing this is that the pluralization rules in English are pretty complicated and are eventually going to trip up either yourself or a user of your code. The guidelines for naming functions are then going to be broadly similar, with the advice that functions should be verbs rather than objects being nouns. Functions should be named in the imperative mood, and for those of you who aren't grammar nerds, this means that they should be written like the start of an instruction in a recipe. This is again for consistency. Having function names in a range of moods and tenses is just going to lead to coding nightmares. As with object names, you should aim to give your functions and their arguments short, evocative names. For functions with many arguments or a long name, you might not be able to fit the definition of that function onto a single line of code. In this case, you should place each argument on its own double indented line, so using 4 spaces to indent, and then place the function body on a single indented line. So this is using 2 spaces to indent. This helps to make it visually obvious where your arguments end and your function body begins. As we mentioned already, there's a lot of case conventions that we might use when naming functions and objects. For people who are used to working in Python, it's often quite tempting to use point separation in function names. And this goes in the spirit of methods from object-oriented programming. Indeed, some base R functions do use this convention, but we're going to recommend against it here. The reason that we're going to recommend against it is that this is actually part of R's own object-oriented functionality, and we don't want to conflict with that. So to summarize this style guide in brief, you want to be naming your objects as nouns, functions as verbs, and adding and using comments to explain the why of your code and give it additional structure. Finally, when you're coming up with all of these names, you want to be using snake case and using appropriate friendly grammar structures. So on top of these naming conventions, the R style guide gives a lot of other guidance on writing code in a way that is kind to future readers of that code. I'm not going to go into all of that guidance in this video, but the motivation for all of these can be boiled down into the following few points. When you're writing your code, make sure you're keeping that future reader clear in your mind. This means using names that are informative and reasonably short. It also means adding white space, comments, and formatting to aid their comprehension of your work. Adding this sort of structure to your code also helps to reduce the cognitive burden that you're placing on that future human being who's reading your code. Next, keep in mind that informative names are more important than short names. This is particularly true when using things like flow controls, which are things like for loops and while loops. Which of these for loops would you rather encounter when you're fast approaching a deadline or an urgent bug fix? Almost surely you'd prefer the second one, where the context is made immediately clear by what we've named things. When we're writing our code, a computer doesn't care at all if you call a variable by a single letter, by a random key smash, or by an accurate and informative name. The computer also doesn't really care if you include no white spaces in your code. That makes no difference when you're programming in R, and the script will run perfectly fine. However, the reason you're doing these things, adding in these friendly practices, is that they can help you when you're debugging your own code, and they greatly help your co-workers when you're collaborating with them. I'd highly recommend you take some time to look in full detail at this Tidyverse style guide and the details it gives about writing clean and readable code. In the final section of this video then, we'll look at how you can make your workflow more efficient by reducing the amount of code you write, as well as reusing and recycling the code that you've already written. This idea of making your workflow more efficient by reducing, reusing, and recycling your code is summarized by the DRY acronym. Don't repeat yourself. This can be boiled down to 3 main points. If you do something twice in a single script, then write a function to do that thing. If you want to use your function elsewhere within your project, then save it in a separate script. And if you want to use your function across projects, then add it to a package. Of course, like with scoping projects in the first place, this is going to require some level of clairvoyance. You have to be able to look into the future and see whether you'll use a function again in another script or another project. This is difficult, bordering on impossible, so in practice it's done retrospectively. You find a second script or project that needs a function that you've already written, and then you pull it out into its own separate file or add it to a package. As a rule of thumb here, if you're having to consider whether or not to make the function more widely available, then you probably should just go ahead and do it. It takes much less effort to do this work now, while it's still fresh in your mind, than to have to refamiliarize yourself with the code in several weeks or years' time. Let's now look at how to implement these sub-bullet points. When you write a function, document it, and when you write a function, test it. So when you come to use a function written by somebody else, you likely have to refer to their documentation to teach yourself or remind yourself of things like what the expected inputs of that function are and how exactly the method's implemented. When you're writing your own functions, you should create documentation that fills this exact same need. Even if the function's just for personal use, over time you're going to forget exactly how it works. The documentation you write should describe the inputs and the outputs of your function and give some simple example use cases. If you're working in a large team, the documentation should also indicate who wrote the function and who's responsible for maintaining it over time. In the same way that we used the here package to simplify our file path problems, we'll use the roxygen package to simplify our documentation workflow. The roxygen package gives us an easily insertable template for documenting our functions. This means we don't have to waste our time and energy typing out and remembering boilerplate code. The roxygen package also puts our documentation in a format that allows us to get hints and auto-completions when using our own functions, just like we do the functions we use from other packages that are written by other people. To use roxygen, it's a bit different to other packages. You only need to install it once, and it doesn't need to be loaded with every library call at the top of your script. After you've installed the package, and with your cursor inside a function definition, you can insert the skeleton code to document that function in one of two ways. You can either use the RStudio menu or the keyboard shortcut that's appropriate for your operating system. On this slide, we've got an example of an roxygen skeleton to document a function for calculating the geometric mean of a vector. Here, the hash followed by an apostrophe is a special type of comment. It indicates that this is function documentation rather than just a bog standard comment. We'll fill in all of the fields of this skeleton apart from export, which we're going to remove. If we put this function in our package, then the export field just makes it available for users of that package. Since we're creating a standalone function here, we won't need the export field, though actually keeping it in wouldn't cause us any problems either. Once we've filled in this skeleton, it might look something a bit like this. We've described what the function does and what the expected inputs are, as well as what the user can expect as an output. We've also given a few simple examples of how the function might be used here, below the examples tag. If you'd like to get some more information on how to use the roxygen skeletons, take a look at the package documentation or the very well written chapter of the R packages book about documenting functions. On top of explaining how our functions should work, we really ought to check that they do work. This is the job of something called unit testing. Whenever you write a function, you should test that it works as you intended it to, and additionally, you should test that your function is robust to being misused by the user. Depending on the context of your work, this might either be accidental misuse or malicious misuse. Finally, you should be checking that your function behaves properly in strange but still valid inputs. These sorts of inputs are known as edge cases. Testing your code in this way can be a bit of a brutal process. You've just created this beautiful function, and now you've got to try your hardest to break it. An informal way of doing this sort of testing might be to first write a function and then play around with it in the console to check that it behaves well when you give it obvious inputs, when you give it edge cases, and when you give it deliberately wrong inputs. Each time you manage to break the function, you can then go back and edit your code to fix that problem and start this whole process over again. While this is testing your code, it's only doing it informally. There's no record of how you've tried to break your code already. And the problem with this approach is that when you return to this code to add a new feature somewhere down the line, you'll probably have forgotten at least one of the informal tests that you ran the first time round. This is going strongly against our previous efforts towards reproducibility and automation, and it also makes it really easy to break your code that used to work just fine. We can formalize this testing workflow by writing our tests in their own R script and saving them for future reference. Remember from the first lecture that these should be saved in the tests directory, the structure of which should mirror that of the source directory for your project. All the tests for one function should live in a single file that's named after that function. To write these tests, one way of doing it would be to write lots of if statements. The test that package can do some of that syntactic heavy lifting for you, and it has lots of helpful functions to test that the output of your function is indeed what you expected it to be. So in this example here, we've got an error coming up because our function returns a logical NA rather than a double NA. Yeah, R really does have different types of NA for different types of missing data. This is really quite a subtle difference. It's probably not something that you would have spotted on your own. And this is really one of the strong benefits of using the test that functions, as well as their nice syntax. If we wanted to fix this test, all we have to do is change our expected output to NA_real_, and I'll let you try that out on your own. We'll revisit the test_that package and some of its functionality in the live session this week, where we'll learn how to use it to test functions within our own R packages. Let's wrap up this video then by summarizing what we've learned. We started out with a discussion of the differences between functional and object-oriented programming, and saw that while R is capable of doing both, data science work tends to have a more functional flavor to it. We then described how to structure your scripts and how to style your code to make it as human-friendly and easy to debug as we possibly can. Finally, we discussed how to write dry code that is well documented and well tested. We've covered a whole heap of ground in this lecture, so thank you very much for your attention, and I'll see you in the next video.